So let's go ahead and pick it up where we left off with the hydro chapter. Chapter 5. See if there's anything we missed here. Yeah, okay, so this is figure 5.9. They call this thing the prime mover, and well, this is actually a mill. This is not a turbine, so you're taking mechanical energy that was put there through the evaporative process, letting the kinetic energy that's of the water flowing downhill and grinding corn in this particular example. And so obviously getting rid of human labor or even animal labor and just letting your technology interact with nature in a way that's beneficial. Okay, so as you can imagine, the first such inventions were not optimized or engineered in any particular way. As we, this figure's not, oh, this is a little tiny figure. Medieval sequia, the diagram comes from the Book of Knowledge of Indigenous Mechanical Devices of Jahazi, Mesopotamia, 700 years ago. So, I mean, it looks like they just had an animal sort of posing as the machine. And you know, who knows? It could have been that it was against the religion to use something other than the animal, or it would look like the thing was possessed if there were not actually an animate being moving the thing. So I don't know all the history behind that, but kind of a interesting little historical side note. Okay, so 3 different types of water wheels. So the overshot, you can see there on the top, you know, fairly self-explanatory. The undershot, and then finally this thing called the breast shot, if you will, where the water comes in right at the center. So overshot, it's coming in and sort of, you know, flowing obviously over into what's called the tailwaters downstream. Undershot, everything's being directed at the bottom. In the breast shot, a little more time for the water to interact with the wheel. Okay, so that's all just purely mechanical systems. The next one that's shown, this is called the Fermions turbine. So water's coming in. There are some fixed guide vanes in the middle. And what the fixed guide vanes do are taking the water that's coming in axially from the top. It's doing more or less a 90-degree turn. These little curvatures, these curved fins, give the water a direction. So if you sort of follow one of these arrows, the water now sort of turning about 45 degrees hits the moving runner blades, and the water is more or less smacking it at a 90-degree angle. So it's not this glancing blow, it's more or less shoving right into it. Obviously, as the water flows out of the device, it's making yet another turn, and there are some fairly sophisticated mathematical models for getting this dialed right in. But the fact that these have been, you know, designed and engineered over time speaks to why these turbine technologies, so in this case you're actually making, you could attach whatever you wanted to this thing, but if you put an electrical generator on the top, you can see why the efficiencies are so great. The velocities, in fact, you know, this is in a lot of ways different from the physics of the wind turbine, which we haven't we haven't covered it. We'll get into the theory behind why a wind turbine can only be 57% efficient. In this case, you know, you have water coming in at some velocity, And you're really relying more or less on the change of potential energy in a hydroelectric dam. You've got, you know, MGH at the top, and then basically zero at the bottom. You're sort of assuming that this water is, even though it is moving, somewhere back in here it's actually going zero. I mean, it's mechanical energy or its kinetic energy is zero. It's all in potential energy. Once it goes through the technology, it's zero again. So depending on how efficiently you make this thing, you know, low friction, well designed, so there's not a lot of turbulence, etc. It doesn't have to obey Bette's law, because you're extracting potential energy rather than kinetic energy, and that'll make sense when we cover Bette's law later. Then of course you have some efficiencies in your generation, but you know, a lot of electrical generators can be up in the 90-95% efficiency range. Okay. So a couple different types of hydroelectric plant. The three basic types, and these were mentioned. You know, different heads, different pressures. This might be something that we would see if you were to do something in the Clark Fork, for example. Relatively low head, just a few meters. You're letting the water flow through, you know, directly through a turbine. If you had something, I don't know, maybe the Como Dam would be high enough. You know, just kind of thinking out loud here, to do something that would be more of a medium head, where, you know, you're building up much more of a dam rather than the so-called barrage. Your turbine's at the bottom. The penstock is more or less the flue. Something like this is going to actually be similar to what's going on at Gordon Butte. You know, some penstock, one going down, the other one going back up. Obviously, in the case of the hydroelectric, it's only down. There's only one path. You're never pumping back. And then again, a high reservoir where you might not have a whole heck of a lot of water. You might not have a very high, you know, a lot of M. You still got the same G and a lot of H, but what you're doing now is designing a turbine that's going to spin at much higher RPMs than either of these two. So that's just kind of a basic category. In each case, you're always trying to maximize power. And just while we're on the topic, and this will have relevance. This will have relevance for 101. In all these cases, the power equals the torque times the angular velocity. So in the case of this guy, you're going to have relatively, well, probably relatively low both, but in general, the flow rate is going to be lower. The cross-sectional area is going to be higher, and so you're going to want to have something that's as high torque as possible in this scenario. These turbines, you can get away with slightly smaller torque because you've got much higher angular velocity. But in any power system, this is what governs. So governs the overall power rating. So it's always a trade-off. Okay, next figure. This is figure 514. Have you guys been to the Hoover Dam before? I've been there a couple times, and I don't know how long ago this was taken, but I remember being there and being astonished by the amount of free, just shoreline there. You know, it was relatively low, and obviously this gets back. The higher the water level, the more the pressure, the more power. But again, you're sort of balancing supply and demand, and relying on nature to fill the thing back up. But you can also see how nature was really working in our favor here with this very narrow gorge. Similar strategy at the Gordon Butte. Someone went out and said, "Gosh, how can we minimize the amount of materials that we have to use, and this was the solution. Really impressive. And you can actually get down into these turbine houses too if you take a tour. Okay, height and pressure. Let's see a little equation there, but if you look at the figure, more or less, at the surface, there at 0 meters, your pressure is 1 atmosphere. You get down to 250 meters, you're at 26 atmospheres. 1 atmosphere being 15 psi or 101 kilopascals. So you can basically take that pressure and determine how much force and thus torque is going through the technology. Okay. So that's what we're looking at in terms of the resource. Okay, and now we can get into the next set of figures. Chapter 5, Part 2. Okay. So really what they're looking at, generator, a couple different things. First of all is mentioned the rate of rotation, that's N. That is equivalent to the omega that I wrote, so another, I can just put that here. And N is going to be measured in RPMs, revolutions per minute, whereas omega is measured in hertz. Next thing to keep in mind is the fact that in Europe they are on a 50 hertz system. The United States we're on a 60 hertz system. So exactly how many times per minute this thing rotates is going to determine exactly what the frequency is. So there are other mechanisms in place to make sure that this is always spinning at some multiple of 50 and that it's phase matched with the rest of the grid. Well, and they also mentioned a little bit estimating the amount of power. We did the same thing earlier in this class, but you know, depending on how many, and they're measuring their rain in terms of millimeters, that's going to more or less dictate what this energy is worth. You know, if it's a lot of rain, it becomes more abundant, it becomes cheaper. If there's not so much, it can become more expensive. Now, types of turbines. Francis turbine up there in the top left. It says by far the most common type. Large-scale plants being used in locations where the head might be relatively low. So you're looking at low RPMs, high torque going through that. Radial flow. So the water's coming inwards. So it's sort of doing that 90-degree turn like it did in the Fermions that we previously saw. The other ones you start to get in that cross flow, the water's acting a lot more like that water wheel that we saw previously. So, and then the Kaplan is something that the pitch is variable, so you can actually maximize the torque depending on what kind of RPMs you need. Okay, so that's just the overall basic designs. Here's some photographs of actual Francis runners. Behind them, some Turgo runners. And again, they're different sizes depending on you know, the flow rates coming through them. All right, this is a 450 megawatt horizontal axis Francis for a small scale. 450 megawatts, still pretty big. 1993. 2 cubic meters per second and a head of 25 meters. Here's the overall structure. And these blades, the guide vanes, are going to be, again, sort of taking on that shape so that the water changes directions optimally to go ahead and turn the runner blades, the moving vanes. Okay. Page 212 talks about the limits to the Francis turbine. It says the available head is an important factor in selecting the best turbine for a particular site. If the head's too low, a large volume is needed for a given power, but a low head also means a low water speed, and these two factors together means that a much larger input is required. Attempts to increase this area whilst adapting the blades to the reduced water speed, et cetera, et cetera. Ultimately, the whole thing to look a lot like a propeller blade, and that's kind of what evolved. So, as the Francis became less effective in lower heads, this is more or less what came up. And these became known as Kaplan turbines. Looks a lot just like a propeller on a boat. The next one that's discussed is with very high heads. The Pelton Wheel is preferable. What's happening in these guys? These cups sort of allow the water to more or less splash through. One thing I heard about the early gold mine, the gold rush, the people making these type of devices were always going to make some money even if the gold miners didn't. Because these type of pumping systems were needed. There's another neat little figure here, I think it's shown in the next slide, that if the water comes in here at the middle at a velocity of V, and then comes out the back basically at zero. Just think of water sort of splashing and hitting a wall. Once it's hit that wall at zero, the resulting velocity of the entire structure is half of that. So you can think of it more in terms of a momentum transfer instead of an energy transfer. Like a ball bouncing off a wall at very high speed. And here's just another variation of that in a turbo turbine. And the water, obviously the water, in order to impart some energy transfer, is going to have to do some sort of, quote, bouncing. It's going to have to change direction. That's, more or less Newton's third law, equal and opposite reaction. Nothing too crazy there. Okay, ranges of application of different turbines. So you can see the Pelton and the impulse that we just mentioned, the propeller and the Kaplan are down here, and then the Francis are sort of right in the middle. So depending on your power requirements, you're going to have different turbine types. Okay. Sorry, I'm kind of rushing through this a little bit, but I kind of get to the end here. So Grand Coulee Dam, Columbia River, 1942. I might have mentioned I'm reading a story where some of the rowers from the Seattle rowing team were part of building this thing. It's a pretty impressive story. The next section, environmental considerations. That's 510. This is proposed Danube scheme. At this point, it's always interesting to go back and look to see whether these have been built or not. But obviously, with the building, you have dam failure could be an option. Plant failures where something gets hot. Silt is another issue. I'm always wondering if there's not enough silt there to go back and do some soil reclamation. It seems like in some ways these dams might be an actual ecological boon if you've got a lot of valuable soils built up behind them. Fish are mentioned. We talked about that a little bit last time. CO2 It said it had been long known that vegetable matter would decay to make CO2, so if you've got sort of a swampy system behind the dam, that can lead to methane production. Social effects are also mentioned here on page 223. And it does cause people to have to leave their homes. So if you were living here before that dam, your home would be lost. This is the Three Gorges Dam. I think this thing's actually been built now. It was only a plan when this was out, but I think the Three Gorges Dam in China is now a reality. 1.13 million people losing their homes. Pretty amazing. The next set of tables show environmental, social, and economic, sort of your triple bottom line, pros and cons. Nothing too crazy there. Let's take a little bit of time. We only got about 5 minutes left, but I do want to look at the economics. So on page 229, there's nothing else. Page 229, what they're doing is comparing, let's get a new little slide going. So page 229, we're looking at combined cycle gas turbine. You're probably hearing a lot about this. There's a lot of gas turbines going on around the planet. It used to be illegal to burn natural gas to make electricity, but now it's happening in a big way. Versus hydro. And you'll see this type of problem when you take 214. You'll see this type of problem, when you're trying to decide whether to ride your bike or take the bus or take your car. You pick your technology, right? But so this combined cycle, you might have a relatively cheap capital going in up front, so 80 million pounds versus 200. So, setting up something to burn methane versus, really doing a big civil engineering project. In both of these cases, let's see if I'm going to make sure. They're both 100 megawatts. So you're comparing apples and apples here. So 100 megawatts. So this combined cycle is actually coming in at less than a pound per watt. This one's at 2 pounds per watt. A lot of times you talk about solar installation. Solar cells are actually under $1 a watt. Wind can sometimes be that competitive. So that's always your upfront capital cost. This guy's going to last 25 years. This one's going to last 60. So now you have to look at the long range payback. This might have a capacity factor of 80%. This one might only be 50%. Because you're never going to drain the whole lake, right? It's sort of rising and falling. This energy is relatively cheap. This one is going to be more expensive, operations and maintenance. But right here, there's no fuel cost. Of course, you have 4.4 pence per kilowatt hour, and then you've got an average output of 701 versus 438. Okay. And then finally, if we go back down, we can see at the bottom the upshot. This is so if you look at 5.7, that was 5.7. 5.8 shows the total hydro cost. So if you had, and again, this is where the time value of money gets kind of weird, but I'm going to write them all out. So 0%. So if money does not cost you anything, so if you say, hey, here's $10, give me $10 back in 10 years. The money didn't cost you anything. Versus, hey, here's $10, sorry, I'm going to need $20 back in 10 years. And that's the way the investment world works. I mean, money is, they sort of talk, the cost of capital, what is it? Well, here it goes, 0%, 5%, 10%, 15%. And now we're going to go the natural gas, CCGT, versus the hydro. So if the capital cost is, the cost of capital is 0, you're going to be paying 5.5 pence per kilowatt hour. And that's right around 10 cents per kilowatt hour. Versus the hydro, 2.78. So it's going to take you longer to get your money back, but the money didn't cost you anything, so it's cheaper. You start to see, oh, well, if the money costs a little more, well, then obviously the cost of the power goes up, 5.8, goes up even more. Well, yeah, it just got more expensive because I'm actually paying for money, not just power. So there's your 6.26. Money gets even more expensive. Here's your 6.77. Well, at 5%, yeah, the hydro also got more expensive. It's at 4.4. It then rises to 6.57, and then, shoot, finally goes all the way up to 8.85. So somewhere, somewhere in here is sort of your break-even point. So you go searching around for money, trying to find a cheap loan so that your hydro is actually truly cheaper. So, and you can get into all kind of economic arguments. Well, we had to kind of plow through pretty quickly there at the end, but it's an ever-evolving field. If you remember back early in the chapter, we talked about how there is tremendous potential for more hydro on the planet. We haven't really tapped all the energy that's out there. So as we move forward, different technologies are bound to emerge. All right. Well, thanks. I'm out of town next week. Tim's going to pick it up from here. Work some more problems. Maybe get into the next chapter and see how far we can get. So hopefully I covered Summary 3 well enough that you can dig back into your old 101 stuff and knock that out.